Good morning, class, and welcome to this lesson on partial derivatives from section 14.1. I want to start out today's lesson with talking about derivatives and how these types of derivatives that are partial derivatives have to do with what we learned about derivatives in Calc 106 or Calc 1. In Calc 1 we talked about the derivative at a point, and we said that if you've got some kind of a function like this, y equals f of x, and you want to know what's the derivative at a particular point, like at point x equals a, then we said we wanted to know how fast the function is increasing or decreasing. And so our motivation was to think about, well, what happens if we pick a number that's a little bit bigger than a and we plug it into the function. And so the change in the function is going to be the change in these two y coordinates. So the rate of change here is going to be the function evaluated at a plus h minus the function evaluated at a, and then we want to know what's the rate of change, so we're going to divide that by the difference in these two, which is just h. All right, and then we want to know what's the instantaneous rate of change, and so we're going to look at what happens to the limit as h approaches 0, and we said that this was the derivative of the function evaluated at a. Alright, so this function, or this expression, gives me the rate of change of this particular function f of x at a point a. Alright, so now what we'd like to do is take that idea a little bit further and talk about, well, what happens if we've got a function f of x and y, and we want to know what's the rate of change of this function. All right, this is quite a bit more complicated situation, because now we've got to talk about, well, it depends on which direction we're going to be moving. And for today's lesson, we're only going to be talking about moving in two directions, in the direction of positive x and in the direction of positive y. And so let's say that we have some kind of a function. Let's say the graph looks something like this. And let's say that this is above the xy plane somewhere. And so it might look something like this. All right, so what we want to know is, if we're sitting at a point here on the graph, what is the rate of change? And I want to know what's the rate of change in a couple of directions. I want to know if I'm sitting down here in the xy plane and I move in the positive x direction, how fast is the function going to be changing? All right, so I'm imagining that I'm moving along this line, and when I do that, I'm going to be moving along this kind of a curve, and that curve is going to be going either upward or downward. Okay, so the idea is, I want to know if this function is f of x and y, I want to know what is the change in the function divided by the change in x. What's the rate of change in the function with respect to x? And the way that we're going to do that then is we're going to think about, if this is a point, let's call this point AB, and I want to move in the positive x direction. So there's going to be another point here whose coordinates are going to be a plus, let's call it h, and the y coordinate stays just b. And so this is how the function, or the variable is changing, or the variables are changing. Only the a is changing, and it's being incremented by some small amount. Okay, so there's going to be a point above there on the graph, and so I want to know how much has the function changed as I move between these 2 points. So we're going to take the value of the function here, which is the function evaluated at this ordered pair, a plus h and b. We're going to subtract the value of the function above this point, f of a and b, and then we're going to divide that by how much have we increased the variable by, and that change is just going to be h. All right, so if you think about this expression is more or less synonymous with the difference quotient up here. This is an average rate of change over the interval from this point to this point. All right, so what we want to know then is, what's the instantaneous rate of change? And so we're going to, again, you look at the idea of the limit as h goes to 0 of this expression, a plus h and b minus f of a and b, and then divide that by h. Okay, this is the rate of change in the direction of x. All right, and then we're going to use some notation. Now, we can't really just use the f prime notation. We're going to call this the partial derivative, and we're going to call it with an f, it's the name of the function, and then a subscript x. And that subscript x just means this is the derivative of the function evaluated at this point in the direction of x. Right, you'll also see your book will use this notation. It's kind of like the Leibniz notation. It's a kind of a script letter D, F, over a script letter D, X. This is, again, the partial derivative with respect to X, and then evaluated at a point AB. All right. Now, we can do the similar thing with finding the derivative with respect to Y. So if we think about starting at this point again, but now we're going to move in the y direction, so we're going to be moving this way. And so when we do that, we're going to end up moving along the xy plane in the y direction, and when we do that, we're going to end up tracing out a curve up here on that surface. And so what we'd like to do is find out what is the change in the function with respect to y. All right, so if I move over to another point here, now the a is going to stay constant, but the b is going to get incremented by some amount. And so the rate of change, or the average rate of change, is going to be equal to the function evaluated at, evaluated at this point is going to be f evaluated at a and then b plus h minus the value of the function evaluated at ab, and then divide all that by h. Okay, so now the b is increasing by h. And then again, we're going to be looking at what is the instantaneous rate of change, and so we're going to attach this with the limit as h goes to 0, f of a b plus h minus f at ab, and then divide that by h. Okay, and so like the notation up here, this is going to be the partial derivative of f with respect to y at ab, and you'll also see your book use this notation, partial derivative of f with respect to y, and then at the ordered pair ab. Okay, so all it is it's a rate of change of the function. It's a limit as the increment of the variable goes to 0. And so for right now, we're only talking about moving in two directions. We'll talk about, well, what happens if we move in other directions later on. But so you've got a couple definitions here. The partial derivative with respect to x at a point is that formula. The partial derivative with respect to y is this formula. And all they are is limits of a rate of change. It's a limit of a rate of change. Okay, so what we'd like to be able to do in this section is be able to approximate partial derivatives by looking at a table of values. We also want to be able to approximate a partial derivative looking at a contour diagram. And then we'd like to get into a little bit of section 14.2 and talk about how we're going to calculate these things exactly, and how we're going to do that with using algebra. All right, so on Blackboard I've got some handouts, and I wanted to mention this earlier. I guess I put it in the email. There are some handouts there that you can follow along and work through these examples with me. You print them out and then you've got them available to you. Okay, so here is a function. F of x is equal to x times y squared. And what we want to know is what is the partial derivative with respect to x at 1, 1. Okay, so what we're looking at doing is finding the rate of change. So this is going to be approximately equal to the change in the function divided by the change in x. All right, and so what I'm looking for is a small increment in x. And we're looking at what's the partial derivative at 1, 1. So here is the ordered pair 1, 1. and the value of the function takes on 1 when x and y are both 1. Alright, so we want to think about incrementing x by a little bit. Well, I've got 1.0 and I got 1.1, so it seems like it would make sense for me to talk about using these two ordered triples. Alright, so the change in the function, we're going from 1 to 1.100, so the value of the function is 1.100 minus 1.000, and then we're going to divide that by the change in x, and the change in x is just going to be 1.1 minus 1.0, and so this partial derivative is just going to give me 0.1 divided by 0.1, and that gives me a rate of change of 1. Okay, so as we move in the x direction from the point 1, and move in the positive x direction, we're going to be going uphill at a rate of about 1. Alright, so now to find an approximation for the partial derivative of y at 1, we're going to do the same thing. This is going to be the change in the function divided by the change in y. Alright, so I'm looking again at this order triple, and I'm looking at, well, what happens when y increases, and so it would make sense for me to talk about these two order triples now. So going from this point to this point, having y go from 1 to 1.05, the function is going to increase by 1.103 minus 1.000 divided by the change in the variable. Now we're talking about changing y. That's going to be 1.05 minus 1.00. So for this one, we're going to end up getting let's see, 0.103 in the numerator and 0.05 in the denominator, and when I divide that, I should get about 2.06. Okay, so what these two numbers tell me is that as I move in the x direction, the function is increasing at a rate of 1. Imagine that we're going uphill at about a 45-degree angle. If I move in the y direction, we're going to be going uphill at a rate of 2. So moving in the y direction, we end up going up at a steeper rate. Okay, so this is just approximations of each of these partial derivatives. Alright, so I can find partial derivatives at a bunch of different points. So on the next page, we're going to be looking at, well, what happens if we want to find the partial derivatives at these ordered pairs? Alright, so to find the partial derivative of f in the direction of x at the point -2, 1, right, again I'm looking at -2 and +1. The value of the function when I plug in those two ordered pairs is going to give me -2. Alright, so again we're looking at the change in f divided by the change in x, and again we're going from this point to this point. So the value of the function at -1.8 happens to be -1.800, minus the value of the function at -2, 1 is going to give me -2, and then the change in the variable is -1.8 minus -2. Right, and when you evaluate this, you're going to end up finding that this is 1 also. Okay, so at this point, the function is also going up at a rate of 1 as we move in the x direction. Okay, now moving in the y direction, we're going to be looking at these two order triples and looking at what happens when y gets incremented by 0.1. So change in the function over the change in y is equal to -2.42 minus -2, and then divided by the change in the variable, 1.1 minus 1. So when I do that, we're going to end up finding that this is -0.42 in the numerator and 0.1 in the denominator, and that's going to give me a rate of -4.2. Okay, so now the derivative in the direction of y, this function is decreasing in the y direction, and it's decreasing at a rate of about -4.2. Okay, so going downhill here, and going downhill steeper than it was at 1, 1. Okay, so that's how we're going to use the table to approximate derivatives. This is really very similar to what we did with planes, but with planes we found out that the rate of change was constant in both directions. We're going to find out that if the function is not a plane, then that's not necessarily true, that that rate of change stays constant. It could change from one point to another like we saw here. All right, so that's using a table to find partial derivatives, or it likes to approximate them. The next thing I want to look at is how would we do this graphically? All right, so I've put together a contour diagram of this same function again. This is x times y squared, and what we'd like to be able to do is approximate the partial derivatives of this function at the point 1, 1 again. All right, so if we imagine what this means, this again is going to be the change in the function divided by the change in x. All right, and we're looking at what is that at the point 1, 1. All right, so at that point, we want to know how fast is the function changing as I move in the x direction. All right, so imagine that we're standing on top of this point 1, 1. The value of the function there is 1, and I'm going to start moving in the x direction. All right, now I think we should probably take advantage of these contours and say if I go from this point, the contour is going to be, or the level is going to be 1, and I'm going to just keep moving across here until I hit the next contour, which is there. So if this is 1 and this is 2, this must be z equals 1.5. So the value of the function there is going to be about 1.5. We're going to subtract the value of the function here, which is 1, and then we're going to have to approximate how far did we move in the x direction. All right, so the x-coordinate here is 1. The x-coordinate here looks to be about 1.5. So 1.5 minus 1, and when we do that, we get about 1. Okay? All right, and if we go back and compare that to the answer that we got using the table, that's exactly the same answer that we got. All right, so now we want to find out what's the partial derivative with respect to y at that point. And so we're going to, again, approximate that with the change in the function divided by the change in y. So again, I'm going to start at this point, and I'm going to move in the y direction. So we're going to hit a contour here. Sorry, I'm at a hotel in Indiana, and housekeeping was just at the door. All right, so anyway, back to our lesson. So we're looking at the change in the function. So going from this contour at 1 up to the next contour, which is 1.5. So 1.5 minus 1, that's how much the function changes. And then we want to look at how much is y changing. All right, so again, we're going to have to kind of approximate this. And so I think if we go across here, we're going to find that that number, if this is 1.2 and that's 1.4, 1.3 is about there. I'm going to call that about, I don't know, 1.23. Okay, and then minus 1. And so we're going to get 1.5 minus 1 is 0.5. We're going to divide that by 0.23. And 0.5 divided by 0.23. If I remember right, I think it was like 2.17. Let's see. 0.5 divided by 0.23. Yeah, about 2.17. Okay? Now, if you go back and look at the first page of this, I think we found out that this derivative was 2. So, you know, those are about the same thing. All right? And we're doing a little bit of approximation here. All right, the other thing we should notice here is that this number 1 is smaller than 2.17, and we can really see that here on the graph, that we said that when the contours are close together, the function is increasing fast, and when the contours are further apart, the function is increasing slower. And so we should be able to see that the derivative in the y direction is greater than the derivative in the x direction. Okay, so that's at the point 1, 1, and then on the next page is we want to be able to approximate the derivative at this other point. So we're going to take the same process and say change in the function divided by the change in x. So we're going to be moving from this point to this point. All right, the change in the function, this is z equals -2. This is z equals -1, so this must be z equals -1.5. And then the value of the function here is -2. And then moving across, this is -2. This looks to be about -1.5. So the change in x is going to be -1.5 minus -2. And again, we're going to get 1. And if you look at the second page of this handout, I think we found out that that was exactly the same values, only we found them using the table. Okay, so as we move in this direction, we're moving uphill at a rate of 1. Okay, looking at the partial derivative with respect to y, again, we're going to look at the derivative, the change in f divided by the change in y. And so we're going to start at this point and we're going to go up to the next contour, so we're going to be moving vertically again. Okay, so the change in the function, going from this contour -2 to this contour that's between -2 and -3, the value on this one must be -2.5. So -2.5 minus -2. And then in the denominator, we're gonna have to approximate how far are we going up here again. And if you look at the value here, it looks like that's a little bit more than halfway between 1 and 1.2. So I'm going to say, let's call that about we'll call it 1.11. So 1.11 minus 1.0. Alright, so in the numerator we're going to get 2 minus 2.5. That's going to give me -0.5. And in the denominator we're going to get 0.11. So -0.5 divided by 0.11. That gives me about -4.5. Okay, and then notice that the numerator here is negative, and so we're going downhill as we move upward on the page here. We're going from one contour that's at -2 to a contour that's at -2.5. We're going downhill, and we're going downhill at a rate of about -4. All right, and if you compare these two answers to the answers on page 2 of our handout, those should be just about the same. I think this was -4.2, and again, we're doing some approximation here, so our answers are going to be off by a little bit. Okay, now moving on, I want to find the derivative of this function, approximating it again, using an increment of 0.01. Alright, so to approximate the derivative here, we're going to have to go back to the definition, and the definition says find the value of the function, and we're going to be doing this at 3 plus h. So 3 plus h is going to give me 3 plus 0.01 and 2 minus the function evaluated at 3, 2, and then we're going to divide that by the change in the function, which is 0.01. Okay, so this is the function evaluated at 3.01 and 2. So if I plug in 3.01 for the x and I plug in 2 for the y, we're going to get 3.01, and that's going to get multiplied by 2 squared, or 4, and we're going to end up with this as 12.04. Minus the value of the function at 3, 2, that's going to be 3 times 4, that's 12. And then we're going to divide that by 0.01. So we end up getting 0.04 over 0.01, and that rate of change then is 4. So at the 0.32, this function is going uphill at a rate of 4. Okay, then if we want to do that same thing here with finding an approximation for the partial with respect to y, this is going to be the function evaluated at 3, and now we're going to increment the 2 a little bit, and we'll have 2.01, and then we're going to evaluate the function at 3, 2 again, and then we're going to divide that by the increment of 0.01. Alright, so if I plug in 3 and 2.01, we'll have 3 times 2.01 squared. The numerator is going to give me 12.1203 minus the value of the function at 3, 2, which is still 12, and then divide that by 0.01. Alright, so when we do that, we're going to get 0.1203 divided by 0.01, and that's going to give me about 12.03. Alright, so the function is increasing at a rate of 12.03 here. Right, and these numbers I think should kind of make sense. As if you think about this function, x and y squared, this function is going to grow pretty quickly, especially as you start moving away from the origin. So as we move further away from the origin, we would expect this function to start kind of growing faster and faster. Okay, now these last two questions get into some of the stuff in section 14.2, but I think you can probably use this technique when you are answering the questions on the quiz for Monday. We want to use the definition to find the exact value of this function. Alright, so the definition says, look at the limit as h goes to 0 of f of 3 plus h and 2 minus the value of the function at 3, 2, and then divide all that by h. Alright, so the function evaluated at 3 plus h and 2, well, the function was xy squared, so we're going to just plug in 3 plus h multiplied by y squared. Well, y squared is just going to be 2 squared, minus the function evaluated at 3, 2 is 12, and then divide that by h, and then look at the limit as h goes to 0. Alright, if we simplify this, this is going to give me 4. 4 times 3 is 12. 4 times h is 4h, minus 12, divided by h, and h is going to 0. Alright, so in the numerator, the 12s are going to cancel out, and we're going to end up with 4h divided by h, and then we're looking at the limit as h goes to 0. These h's are going to cancel out, and we're going to get 4. Alright, which is the same number that we got up here, and I think that we shouldn't be surprised that those numbers are the same, or at least close to each other. So what about finding the derivative in the y direction? We look again at the limit as h goes to 0, but now we're going to increment the y value. So this will be the function evaluated at 3 and 2 plus h minus the value of the function at 3, 2, and then we're going to divide that by h. Alright, so the function evaluated at 3, 2 means plug 3 and 2 into xy squared. So we get 3 times 2 plus h quantity squared minus the value of the function at 3, 2 is still 12. And we're going to divide that by h and look at the limit as h approaches 0. Alright, so simplifying this, 3, if we square this, we're going to get 4 plus 4h plus h squared minus 12, all divided by h, and h is going to 0. More simplification, 3 times 4 is 12, plus 12h plus 3h squared minus 12, all divided by h, and h is still going to 0. Alright, so up here these 12s are going to cancel each other out. We're going to be left with this expression, and in that expression we can factor out a common factor of h, and we're going to be left with 12 plus 3h over h, and h is going to 0. The h's will cancel, and we're going to be left with just 12 plus 3h, and then as h goes to 0, this thing is just going to end up approaching 12. Alright, so and if we compare that number 12 to the number that we got up here by using an approximation, we see that those numbers are pretty close together. Alright, so again, just to kind of recap things that we did here, the partial derivative with respect to x is the rate of change as we move in the x direction. Okay, by definition, it is this formula. the change in the function divided by the change in the variable, and then we're looking at the instantaneous rate of change. So we're incrementing x here. Down here we're taking the derivative with respect to y. We're looking at how does the function change as we increment the y slightly. And then again, the notation, I'm usually going to use this fx and fy notation, but keep in mind that your book is going to also use this Leibniz notation in a couple different places. Okay, so you should be able to get through section 14.1, and again, we did spill into a little bit of section 14.2, and you are probably going to need those 14.2 techniques on that last problem to do a couple of questions that were on the quiz on the back side. All right, so I hope this has been helpful for all of you, and I will see you guys on Monday, and have a good weekend. All right, thanks. Bye.